All right, let's see who's alive and who's not. Painting on that camera tab also. Let's pop this up. So what are we after here? Put your name in the chat box as always. You need the applied one textbook. Right, so that's what you're going to need to start with. It's all very much. Ugh, it's annoying. I hate it when the plastic crinkles. Right, cool. Just what you're after. Put your name in the chat box, please. And get the pure and sorry, not the pure. Get the Mechanics and Statistics first year book out. We're going to be looking at chapter 4 as requested. Bear with me just a moment. All right, so good morning to everyone. Thank you very much for your prompt entry. Kelvin, Eman, Reba, and She. Okay, cool. So, Eman, last lesson, as I mentioned, we are going to do some recaps. Well, a lot of the time we're going to spend this term doing some recaps, this half term anyways, of last year's, well, not last year's, this year's content. And one lesson of the 3 will be done on differential equations. And that differential equation one will be done at 10:45. And Eman, sorry, someone had a new name there. Eman has asked for chapter 4 on applied. So that's the pure and statistics. Sorry, it's not the pure statistics, it's the statistics and mechanics book. So what I'm going to do is go through that, give you some exercises on that. It's not going to take particularly long, but I do want to flick through it, make sure that that's something we're comfortable with. All right. So the book you're going to need now is the Applied 1 textbook. I'm just pulling it out myself now. You should have all the textbooks. Again, you've been advised countless times at this point to make sure that you've got, good morning, whoever that was, that you've got all your textbooks in one place as PDF files and can access them quickly, depending on whatever I choose to do that given day. All right. You will be sent a new textbook today, if you haven't been already, along with a PowerPoint. So that'll be another one to add to your collection. Put it in whatever file, whatever file you've got for this, put it in that file. But that won't happen until about 10:45. Okay. So the page, chapter on that we're looking at is, just bear with me a moment. I haven't used this computer since yesterday, so it's been a bit slow. It's chapter 4, correlation. It's very, very simple. All right. It's only 2 exercises in a mixed. So it's chapter 4. It's called correlation. It starts on page 59, and there's 3 exercises. There's a 4.1, 4.2, and a mixed exercise. All I'm going to do is I'm just going to go through that chapter with you. So if you can take the next minute or so to get yourself the textbook. So it's the applied one, which is the statistics and mechanics. First year, not second year. I mean, you have the second year, you might do it. And it's chapter 4. And it's a very, very short chapter. The reason why it gets finished in second year, which obviously we're not going to do today. I'll cover the content. At 10:45, it's going to be a little bit more interesting because what we're going to be doing is the differential equation stuff, and that is going to get very spicy very quickly. What are we doing next lesson? Differential equations, further maths version. All right, so that's going to be a lot harder. All right, okay, cool. Let's move. We move. So correlation, it tells you if you go to page 59, sorry, yeah, 59 it is. There are 4 objectives. Number 1, be able to draw and interpret scatter diagrams. You have to do that from secondary school. Number two, interpret correlation and understand it does not imply causation. Again, it's something you learn at GCSE. I'm going to cover it again. I'll cover it myself. All right. But those are two things you should already know. Interpret the coefficients of a regression line equation for bivariate data. Okay, cool. We need to be able to do that. It's not a very difficult thing, but I'll show you how to do it. And then understand when you can use a regression line to make predictions. All right, so those are your 4 objectives. Where would you find those objectives? You find them on page 59. All right. So if you want to know what we're doing, that's what we're covering. I'm not going to propose copying them out for you because it's like loads of words. But the objectives of today's lesson are on page 59. All right. Okay, let's roll. Let's just get this done. Sorry, I do apologize. It's taking a little longer than I hoped. There we are. Okay, so what do we need to know about scatter diagrams? Not a lot, really. All right. So I'm just going to give like a heading, scatter diagrams. I'm just going to give you the information you need and how they work. Okay, first of all, they are bivariate graphs. What does that mean? There's 2 variables. There'll be something that goes on the x-coordinates, something on the x-axis, and something going on the y-axis. So it's 2 variables. So just be aware of that, right? So for a scatter diagram, you've got 2 variables, right? And each variable's got a name, yeah? The one that gets plotted as the x kind of values, or the x coordinates on the graph, is called the independent variable or explanatory variable. So the independent stroke explanatory, they both kind of mean the same thing here in this context, is the one that goes on the x-axis, or the x was plotted, yeah, on the x-axis. And then the second one is the dependent or response variable, and that's plotted on the y-axis. Okay, so you're going to need to know what those words are. And then we're going to talk about correlation. I'm going to do a quick example of this, but then we'll move on to the second part of all this. So can you copy those words out if you haven't already? Make sure you memorize them. You need to know what they are, right? Because when we do kind of discussions of, when you're asked 3 marks, tell me something about the graph, you need to be using the proper mathematical terminology. So I'm hoping that's making sense for people and not too onerous of a thing. All right? And as soon as you finish copying out, can you pop in the chat box? And then I'll move on to the next step. Done. Brilliant. Cool. A lot of people are done. I'm going to give it a few more seconds, and then we're going to move on. All right. Right, beautiful. So I'm going to give you an example here. I'm going to use that to illustrate the next thing I'm going to teach you about, which is correlation. So imagine you are running I don't know, let's say a concert hall, yeah? So something like the O2. And you wanted to see how much drink sales you have depending on the temperature of the building, all right? So the temperature of the building I'm going to give here, temperature, and then drink sales in thousands, yeah? So I hope you understand what's going on there. So you're in charge of the O2. You want to see how much drink sales change if you change the temperature, all right? So let's say for some reason you don't have any heating at all. You sell maybe 20, all right? 5, not a lot more. 10 starts to pick up. 15, again big. 20, up to 50. 25, 70, and say 30 is 100, right? So which one of these is the independent variable? It's obviously going to be the temperature because that's the one you're controlling, right? The dependent variable relies on the independent variable to have a change. Yeah, the temperature will be the independent variable. The drink sales is the dependent variable, the response variable, all right? So let's do a quick sketch of this, and then we start talking about correlation. It's going to be a very rough sketch. There's not any kind of diagram to scale, and I'm going to redraw that so you can actually see it and all the rest of it. So you've got 0, 5, 10, 15, 20, 25, 30. Now, obviously, if you're going to have to draw a graph, they'll give you a scale in the exam. Also, if you're going to draw a graph, do it better than this. 20, 40, 60, 80, 100, right? So your independent variable goes on X, and your dependent variable goes on Y. Simple as that, right? I will move the graph. Well, I mean, because you know what the scale is. I don't stress too hard about the fact that you can see the scale or not. Try not to knock the thingy off there. Right, so this is what you've got. So the first one's a 0, 20. Right, fine. You pull up that. I'm going to put that on there, so that is 0, 20 there. 5 is 22, so not a great deal of difference. 10 is 28, slightly higher. 15 is 30. Again, slightly higher, but not massively. Again, the diagram doesn't have to be... When you draw it, it has to be good. But if I'm doing it on a whiteboard, you know, there's a little bit of tolerance you need to have there. 20 is 50. 25 is what? What did I say? 70? So there. And then 30 is 100. And one thing about scatter diagram is you don't join the points up. You do a line of best fit, all right? So when you've got a scatter diagram, to draw the line of best fit, let me just move on. That involves a little bit more mathematics than you're used to, all right? And I'm going to show you what happens after that, right? But before we go on to doing lines of best fit, let's talk a little bit about correlation. What kind of correlation does this graph show? Can you pop it in the chat box for me? All right? So pop in the chat box. What type of correlation do you think that graph shows? Positive. Nope, I do not want to do that. It's definitely not no correlation. It's clearly a positive correlation. It's pretty strong. Yeah, it's a pretty strong one. I would say it's realistic. It's a strong correlation. Yeah, I mean, so I'm just going to do a quick sketch of what correlations look like. In fact, the textbook does it better for me. Can I guide your attention to? I'll give you the exact page. For flip's sake, go away. My laptop's going to pay. I think what would happen to my teaching, my laptop broke. If you look on page 60, so page 60 is the one, midway through, there's a better set of diagrams than I'm drawing, put it that way, because I can't draw. So page 60 is the one, have a look and see what correlation looks like. Hello, Zara. Okay, cool. So far so good. Hopefully you can all recognize what positive, what negative correlation means. What do they mean? I mean, there's two things you need to take away from this. So page 60 is what you're looking at to look at correlation. There's two big ideas you need to get. What does correlation mean? It means that there seems to be a relationship between one variable and the other. As one goes up, so does the other. As one goes down, so the other one goes up. So there's two different types of correlation there. So you've got positive and negative, right? And that's rubbish because you can't see it. Positive and negative. So for the positive correlation, as the independent goes up, so does the dependent. Yeah? And then for the negative, as the independent goes up, the dependent goes down. And if the independent went down, the dependent would go up. Okay? So those are like how positive and negative correlations work. So for a positive correlation, if the independent goes up, so does the dependent. Vice versa. If it's negative, they both go down. But if it's negative, they go in different directions, all right? And they look different. And where will you see the pictures of them? You'll see them on page 60, all right? The other thing which is really important, I mean, this is almost like to the point where it's a mean in statistics. Correlation does not imply causation. Here's a very, very simple example, right? Since, I don't know, let's say 2020, yeah, there's been a new iPhone. I think it's a slightly cheaper one, right? Also, coronavirus has come. Is there a correlation? So is there the fact there's a correlation between sales of the new iPhone and coronavirus cases mean that iPhone sales cause coronavirus or coronavirus causes iPhone sales? The answer is no. You can have two things that are correlated, but it doesn't necessarily mean that one person or one thing causes the other. Another one, that's the one I always usually use, is the number of pirates have fallen because global warming has increased. Both of those things are true, yeah? But there are less pirates in the world now, and there's been global warming. They're both true, but they haven't kind of caused each other. Do you get what I mean? It's just happened that two different things have happened at the same time. And you've got to be really, really careful, because correlation does not mean that one thing has caused another. Yeah? I mean, Kelvin gives an example of 5G. I mean, similar example there. 5G has started in some places, and coronavirus has started. Does that mean 5G caused coronavirus? The answer is actually no, because in Iran, there is no 5G, but there is coronavirus. So you've got to be careful with this stuff. All right? So there's that. Correlation does not imply causation. If you want to try and show that one thing is causing another, exactly so. If you want to show that that one thing is causing another, try and establish something called a chain of causation. I mean, this isn't really maths. This is like for when you do stuff in the real world. So if I wanted to say that increasing, like take the previous example, increasing the amount of temperature in the O2 will make people buy more drinks. You can sort of see that people are going to get hotter. They're already presumably like doing whatever events going on there, so that they'll be reasonably active. So there's an easy chain of causation that's believable. Yeah. If I tell you that global warming and pirates are inversely correlated, you've got to explain to me why would the number of pirates make the world hotter or colder? Yeah. And that's a lot harder to sell. Anyways, let's move on. Last bit of today's lecture, today sort of is a lecture this week, is TMCC, which you don't actually have to calculate yet. So linear regression is your heading. It sounds super complicated, but it's not. Next year it gets super complicated. Even then, it's not really super complicated. You have to do something to calculate. But you know, this is pathetic. It looks super complicated, right? All it is, it's saying we've not, you know, like you had lines of best fit before. You just used to draw your line of best fit that goes through as many points as it can, and it's got roughly equal number of points either side, and all that good stuff. Here they're going to say, we're going to show you how to make a line of best fit with an equation. All right. But the thing is, they're not going to actually ask you to work out the equation generally. Not this year anyways. Yeah. Next year they will. Okay. So I'm going to take you through exercise 4B, question 1. And that's actually just going to teach you enough of the content, right? That you I mean, if you look at it, linear regression starts on page, wait, I'll get it for you, page number. Yeah. Come back. It starts on page 63, and it looks absolutely insane. There's like squares flying everywhere. Bloody hell. But you don't need to know any of that. That's the interesting thing. Yeah, there's not a lot there you need to actually know. And I'm going to take you through question 1, and that will pretty much cover what you do need to know. I'm just going to check that string in case there's any kind of super psycho questions that are hidden. Okay. Yeah, so I'm going to go through question 4B. I'm going to go beyond 4B. No, just do 4B actually. 4B question 1. That's all you're going to need. And then I'm just going to ask you to do the mixed exercise. So your work today is the mixed exercise. All right? Until 10:30. 10:45, I'm going to be back with differential equations, which is going to be a big step up in challenge, right? Even for me, I should really look at it. I'm not going to, which is more fun, but I should have a quick look at it before I go. All right, we good? All right, let's do this. So the example I promised you was 4B question 1. Yeah, I'm just going to finish one example for you, and then you're going to do mixed exercise on 63. That's right, yeah. There's not, by the way, the mixed exercise isn't on 63. It's on 60, what? 66, actually. So I'm going to do 62, question 1 from page 63. You do mixed exercise on page 66, if that's not clear. Let's roll. Let's have a look at 4B1. I'm not going to do part A. I presume you can draw a scatter diagram at this point. Okay, so I'm going to start from B, C, and D. The equation of the regression line on P on N is P equals 21.0 plus 0.98 N. Interpret the figures of 21. What does 21.0 mean in this context, and what does 0.98 mean in this context? Okay, so in this context, you've got an equation of a line. So basically, this is the equation of your line of best fit, or your regression line, the equation of your regression line. All right? And your regression line, this number here is C, the y-intercept. Yeah? So 21.0 is your y-intercept. And why do I care about that? Because your y-intercept tells you what happens when you haven't made any items at all. All right? So when n is 0, so n is number of items, p is 21. Yeah? So that means even if this company literally makes nothing at all, it would still have production costs of £21,000. Yeah? Because it says 21 and it's in thousands. All right? Why would that be? How does that make any sense? Not make anything how they, that'd be wages, wouldn't it? Logically. Yeah? What does 0.98 mean? It means that's your gradient, and that tells you how, if you add 1 to the number of items being made, suppose you make 1 item, yeah? How much more would you have, production costs would go up? So every time you make, 1,000, it's not 1, it's in thousands. If you make 1,000 more items, you have to pay £980, all right? Because 0.98. Every time you add 1,000 new items, you have to pay another £980 in production costs. So that's the definition of the numbers, right? As I said, I'm not doing it. I'm also not going to do B because it's like draw a line. I hope you can plot an equation of a straight line by now. If you can't, you probably should contact me, right? So question C and question D is what I'm going on. So what I'm doing is I'm looking at it as an equation, a line of best fit, and then I'm thinking about what it is, yeah? So this guy is what happens when literally x, in this case n, is 0. What is this? This number here tells you if I go across 1, how much does the other variable go up or down? Yeah, and then I've read along into the question, exercise 4B1, to know I'm talking about items and costs. All right. The company expects to produce 74,000 items in June and 95,000 items in July. Comment on the suitability of the regression line equation to predict the production costs in each of these months. Okay, that's really important because it comes across something that two different ideas that you need to know about: interpolation and extrapolation. But they're not difficult. You just need to be able to read a table. So the first is 74,000 years. So by the table numbers, you'd write 74 for n, yeah? 74 is fine because it's inside the data that you've had before. So you've had years when you've had 15, you've had years when you've had 81. So 74 is not out of the ordinary, yeah? And you've got 75s, you've got 81s, you've got some numbers that are bigger than 74. So if you want to make an estimate for 74,000, which is 74, you're fine because your data covers that, and that's called interpolation, all right? But when you go to 95, you've never, this company has never built 95,000 items before. There is no data for anything like 95. The closest is 81. That's called extrapolation, and it's less reliable. All right, it's less reliable because you don't know whether the line of best fit carries on working like that, right? You don't know if it carries on being a straight line ad infinitum, right? You've got no evidence for that. It might be that like they can only make 90,000, and then if they're going to make another 5,000, they have to open up a whole new factory. You have no evidence for that, right? Do you know what I mean, right? So interpolation is more reliable because interpolation is something that you've seen happen before, right? You've seen something larger than that has happened before. So you can feel like, you know, it's worked for like, I know this model's worked for 81, it'll work for 74. But knowing it's worked for 81 doesn't mean it will work for 95. You've got no evidence of that, okay? So that's the difference between interpolation, which is a bit more reliable, and extrapolation, which is less reliable. Doesn't mean you can't do it. Sometimes you have to, right? I mean, sometimes you just, you know, you're going to have to do something new and you have to have a best estimate. I'm not saying never extrapolate. I'm just saying it's less reliable, okay? So now all I'm going to say to you for the rest of the next hour, and this is till 10:30, do the mixed exercise. Remember what the rules are. I need to have your work emailed to me by end of today. Yeah, by end of today. So the mixed exercise, page 66. I'm going to shut this off now in about 2 or so minutes. Anyone got any further questions, let me know. Check your emails about 10:45. I'm going to be on the live chat. I'll be on YouTube. All right? At about 10:45. I mean, give a minute or two either way, depending on like Wi-Fi connection and stuff like that. You know, these things happen. Okay? So I'm going to give about another minute and a half. Anyone's got any questions, great. If not, you can go, just do the exercise. I'll see you at 10:45, all right? Beautiful. Right, while you're doing that, seems like everyone's turned up. I've had word from Marilla. So I'm going to do the register. Yeah, register. Zilch. I didn't ask for that. I told you late. See this late. I can richly deserves that. Four videos there.